All right, guys, so this is Lab 8, ECG, electrocardiogram. A lot of this stuff I've already been through in the other lecture that I made for your activity that you have to do, but I'm just going to try to get this to be as short and sweet as possible, get you the information you need so you don't have to sit here for forever watching videos. All right, so briefly, heart anatomy, two atria, two ventricles. The right atria and the right ventricle deal with deoxygenated blood. Right atria receives the blood, pushes it into the ventricle. Ventricle pushes it out into the lungs. And then the lungs bring it back through the left atrium. The left atrium pushes it into the left ventricle, and the ventricle pushes it out to the rest of the body. The myocardium, it's a little bit different from skeletal muscle. I've already talked about this a little bit before in the heart rate and blood pressure lecture, so I'm not going to talk about it more. But basically, in addition to what I've talked about before, there are pacemaker cells or autorhythmic cells, and the heart is special in the way that it doesn't need external stimuli for contraction. It has its own stimuli for contraction, and that is produced by these pacemaker cells, particularly the SA node right here. The SA node will depolarize the heart, and it begins at the atria, and then it will go down and depolarize the ventricles. This is another picture of it, but this kind of goes into more depth of what is happening during an EKG. So the SA node fires right here, and then the atria start to contract, start to depolarize and contract, and that's this P wave right here. And then the ventricles will then depolarize and contract, creating this QRS wave. And then from S to T, that is repolarization of the ventricles. This is what it looks like. You can see it on the EKG as it's contracting. It might be a little bit fast for this, but it's just a general idea of what it looks like. So the cardiac contraction is slightly different from the skeletal muscle contraction. And the reason why it's different is because you don't want your cardiac muscle to contract immediately after it has already contracted, because then you would have an irregular rhythm. So this is the cardiac contractile graph, and then this is the skeletal muscle represented here. You can see that the cardiac has this kind of plateau and then dips down. And this plateau basically what prevents the cardiac muscle from contracting immediately after it is contracted before. It prevents it from depolarizing as soon as it has already depolarized, unlike the muscle where it can start to depolarize sooner. So here's a picture comparing the contractile action potentials to the pacemaker action potential. Pacemaker action potentials, they don't want to reach this phase where they level off because they need to depolarize again to make the heart contract again. And that's how this phase right here is how the pacemaker cells are pacemaker. This is how they can contract on their own, and they don't need external stimuli to send signals, to send the action potential. What are EKGs? EKGs are basically one way that we can look at the heart and how it functions. And we can use these waves to determine how the heart is contracting and how it's functioning. Since the heart is a muscle, it requires electrical signals to function, and we can read those electrical signals through the EKG. I already went over this in 2 videos, so I'm not going to go over it again, but you can take a look at this and pause the video if you want, just as a refresher. I went over this in the How to Interpret EKGs lecture. But briefly, the limb leads basically look at different directions of the heart in the frontal plane, while the chest leads will look at different parts of the heart through a horizontal plane. And this is where I would have you guys put EKG stickers and leads on each other, but maybe you can do that at home. All right, so I already went over this in the interpreting EKG lecture, but I will briefly go over this again. Each one of these boxes is 0.2 seconds long, each one of these big boxes, and each one of these little boxes is 0.04 seconds long. And you can use this to determine different rhythms of the heart and arrhythmias, and you can determine heart rate through these EKG boxes. The most accurate way of determining heart rate is through the R to R interval, but you can only use this for a regular rhythm. And basically, it's the number of small boxes, these little small boxes, times 0.04, and you use 60 divided by that number that you found, and that's going to be beats per minute. So just an example, we can determine the heart rate of this EKG strip. We're going to find the R wave that is closest to the beginning of one of these big boxes, so like this one. And each one of these big boxes have 5 little boxes in them. So we'll count 5, 10, 15, and then 16, 17, 18, 19. So 19 times 0.04 equals 0.76, and then 60 divided by 0.76 is about 79 beats per minute. I'm going to briefly go over this. Regular rhythms, the R to R intervals are consistent between all the R waves. Irregular rhythms are when the R waves are not regular, so they're not equal distance apart. Some can be closer, some can be longer. It is an irregular rate. Irregularly regular is like there's a pattern, so these 3 are kind of clumped together, and then there's a space, and these 3 are clumped together, and then there will be another space. Irregularly regular is when they're all irregular, so there's no pattern or anything like that. To determine whether or not a PR interval is regular or irregular, regular is between 0.12 seconds or 0.20 seconds, which is basically 3 boxes, 3 to 5 small boxes, and anything out of that range is irregular. QRS complex, if it's greater than or equal to 0.12 seconds or 3 small boxes, then it's a wide QRS. ST segment elevation and depression, basically if it's 1 small box elevated or one small box depressed, then it might be ST segment elevation or depression. And you compare that to the isoelectric line right here, and this one is definitely got ST depression because there's more than 1 small box that it is below. And then same with this, ST elevation. This is more than 1 small box above the isoelectric line. All right, so I hope this helps you with the activity and helps you with the rest of your lab write-up. Let me know if you have any questions. Stay safe.